So, let us start this lecture with a thought process. Love is the one kind of eternal energy that is being possessed by each living being. I call it basically is the internal energy of a human being. So, let us recall that in the last lecture we are talking about basically mixtures which are not reacting, and we will be discussing about the psychrometry. The psychrometry is basically a process by which we can analyze the moisture content in the air, right? And also find out how we can make it, analyze that. That process is psychrometry. First, we will be taking up non-reacting mixtures, right? Because if some mixture of gases are there, then it is not reacting. So how we will handle it? So in engineering, we encounter mixture of gases very frequently. We have seen not only we are surrounded by the air, which is a mixture of gases like oxygen, nitrogen, argon, and even we are producing carbon dioxide kind of things. But we also handle several mixture of gases, right, in engineering applications. We have seen the heat engines and other things, like there are several gases, particularly gas power cycle we have seen. So, as I told that air is a mixture of pure substances like nitrogen 78.1% and oxygen is 20.95%, and then argon and carbon dioxide are very less, and other trace elements will be there. So, if you recall what is a pure substance, we have already discussed earlier. It is basically the matter which is homogeneous in nature and remain unchanged, with its chemical composition, right? That we call it as a pure substance. And the homogeneous gas mixture, basically, which will be undergoing, right, reaction, we cannot call it as a pure substance, right? Can we? We cannot really call it. But if it is, there is no reactions, right, or after the reaction, before the reaction, we can also consider the pure substance. And properties of such mixture can be determined just as the properties of the individual components. If we know the properties of individual gases, then we can find out, and then we will have to find out mixtures. Therefore, we need to learn how to handle the mixture properties, right? And we will be considering the ideal gases, right, most of the time, because of we are not handling a very high pressure, and even if we are handling the high pressure, we are not handling very low temperature, because if then only it will be real gases comes into picture. But we will be using ideal gases most of the time because of it is handy to use, and also we learn how to use ideal gas law and using the compressibility factor into that for the real gases. So there are two methods of analyzing this mixture of ideal gases. One is mass analysis, other is mole analysis or molar analysis, right? And let us consider that there is a container, which contains, let's say, certain amount of gas. Like if you look at, there is a container, it contains, let's say, Na molecules of gas, and then Nb and Nc, and then several n number of gases are there, it contains. So how will basically do that? We can do mass analysis of the mixture of ideal gases by considering the total mass of the mixture will be basically equal to the sum of the masses of constituent gases, right? Which we know, like basically that is the m, that is the mixture mass, is equal to mass of the A component of gas and plus mass of B plus mass of C, and it goes on. That might be nth types of gases, and which is nothing but summation of mass I. I can be 1 to n. So, if I will divide this like by mixture mass, right, m over here, m over here. So, what is this one? What do you call this one? This basically mass fraction, right. This I can call it as a XA, that is your mass fraction, and similarly XB will be mass fraction of the gas B, and XC will be the mass fraction of the gas C. So, therefore, if you look at the mass fraction of all gases, sum over that is equal to 1. That is the things what we can see. So, I mean, this is the one which you people might have learned earlier. I mean, I am just repeating for the sake so that you can recapitulate those things. And similar way we can look at also the mole fraction, right. So, that is the molar analysis. The total number of moles in the mixture Nm is equal to sum of number of moles of each constituent of mixture, that can be expressed as basically Nm is equal to Na plus Nb and plus Nc goes on till nth one. I can divide this thing by Nm across, right. So, that this is nothing but your mass, what you call mole fraction, that is Ya, and similarly this can be Yb, and this is your basically mole fraction of the Is species, right. I can be anything. So, what this equation says, that the summation of mole fraction of all species is equal to the 1. So, but we need to now relate this mass to the mole through the, of course, the molecular weight, and that is Mi is equal to Ni MWI. MW is the molecular weight of the gas of Is species. So, we can write down basically this MM is a summation of all the masses of constituent gases, and that is equal to Ni MWI. And if I divide this equation, what you call by moles, right. If I divide by this total mixture moles, right, and M, so I will get, and if you look at what is this one, this is basically the mole fraction of A. Similarly, this will be mole fraction of B, and similarly mole fraction of nth species. So, if you look at the molecular weight of the mixture is basically the mole fraction of the species A into molecular of species A and mole fraction of species B and molecular weight of species B, and it goes on for the nth species. That is nothing but summation of the product of molecular weight of the Is species into mole fraction of the Is species, right. That is the things what you can find out what is the molecular weight of the mixtures very easily. And by this way we can also relate the mass fraction with the mole fraction through the molecular weight. If you look at this is your mass fraction of Is species, and this is your mole fraction of Is species. So, you can relate this through the molecular weight of the mixture and Is species. So, if you look at the behavior of the ideal gas mixture, we can use the ideal gas law by the which is nothing but PV is equal to N RUT, and which we have already discussed extensively. And question arises whether we can use the ideal gas law when two or more ideal non-reacting gases are mixed. Definitely yes, we can do that. And for example, we will be handling several gases of what you call ideal gases, and as we know that air, which consists of several ideal gases like oxygen, nitrogen and argon, carbon dioxide, can be easily treated as an ideal gas provided its composition behaves individually as an ideal gas, then only we can do. Then we can analyze this mixture very easily by using two models, like one is basically Dalton model, or other is the Amagat model that we will be discussing. So if you look at the Dalton's law of additive pressure, you know very well, just for the sake of it I am just repeating it. The pressure of an ideal gas mixture is equal to the sum of the partial pressure, right. What is that partial pressure? Partial pressure is basically pressure exerted by the individual component, right, when it exists alone at the same volume and temperature of the mixture. For example, if I take this air, right, at certain temperature, ambient temperature, let us say TA, and pressure PA, right, it is condensing, let us say three gases we are considering, nitrogen, oxygen and argon. Now, if we keep the same volume, right, and same temperature, then it will exert a pressure, what we call it as a partial pressure, right. We generally use a smaller p, right, for the partial pressure, right. And similarly for the oxygen, if like partial pressure, it will be when it is maintained at the same volume and the same temperature, so also the argon. So if you look at, we can generalize it, that is the mixture pressure will be nothing but what you call like Nm RUTm divided by Vm. This is from the ideal gas law, and we know that Nm is equal to nothing but Na plus Nb plus nth gases, and if you just separate it out here, so if you look at here, Na RUTm divided by Vm is nothing but your partial pressure of A, and this is partial pressure of B, and this is of course the partial pressure of nth gas. So and that is I have written here, and keep in mind this partial pressure A is basically dependent on the number of moles of A, universal gas constant, and the temperature of the mixture and also the volume of the mixture. So similar way, basically we can say that Pm is nothing but summation of partial pressure of the number of gases whatever it will be constituting. So for air, what example we have taken, P air is basically summation of three partial pressure. In this case we have considered nitrogen, oxygen and argon are the constituent of the air. So we will be looking at basically what are the limitation of Dalton's law. If you look at the Dalton's law, basically assumes that the molecules of individual component are not influenced by the pressure of other component of the mixture, which need not to be true, but we assume that way and then do that. And keep in mind that this Dalton's law is only valid for an ideal gas mixtures, for it won't be really can be valid for the real gas, but however we can use it for the real gas mixture. In the process, of course, we will have to tolerate some moderate amount of error and within certain pressure and temperature range, right? And beyond that we cannot really use the Dalton's law for the real gases. As a result, it will incur, because of it will be incurring the more amount of error. Because see why we can't use this Dalton's law for the real gases at a little higher, particularly higher pressure and low temperature. There will be significant intermolecular forces in real gases at high pressure and low temperature. Therefore, it cannot be used. And so we look at now Amagat's law of additive volumes. And in this case, what we do, we just put other way around. That is, like we keep this pressure of the mixture constant and also the temperature. But however, the what we call volume occupied by the individual gases will be different. For example, if we consider the air, which is at the mixture temperature and the mixture pressure, contains VA amount of volume, right? And then if you look at the nitrogen and the oxygen and the argon, the volume will be different. So we can write down the total volume of the mixture of gases. In this example is the V air, so is equal to summation of the volume of the nitrogen gas, oxygen gas and argon gas, provided that mixture pressure and temperature is remaining constant, right? And that is nothing but your what you call Amagat's law of additive volume. We state that the volume of an ideal gas mixture is equal to the sum of the volume of each individual component gas that would occupy if each gas is existed alone at the mixture temperature and pressure. In other words, what is being said, I am just stating again that mixture temperature and pressure will be remaining constant, right? And in case of Dalton's this thing, what is remaining constant is basically the temperature and the volume, right, for these things. And here it is just other way around, that is temperature and pressure will be remaining constant for same as that of all the individual gases. And you can write down that Vm is basically from the ideal gas law NMRU Tm divided by Pm, and we can take this Nm is nothing but a summation of Na plus Nb plus nth gases, right? And if we do expand these gases, and then we will get that this is nothing but from the ideal gas law, this is nothing but your Va, volume A, and this is volume B, right? Of course, this is the volume of nth gases. And that says that the summation, the mixture volume is basically the summation of all individual gases, right? So now if you look at we can talk that in terms of like Va by Vm, and Va we have seen is a function of number of moles of A and Tm and pressure, is we can divide this by the Pm and then multiply it by these things, right? And if you look at this Va from the ideal gas law is equal to Na RUTm divided by Pm, and the Vm we can express in terms of Pm divided by Nm RUTm, and this Ru will cancel it out, so also Tm, and if you look at the Pm will cancel it, and what you will get is basically the mole fraction of A, right? And similarly, as a result, we can find out this volume is nothing but of A is equal to mole fraction of A into mixture volume. And similarly, we can also find out the pressure ratio, that is the partial pressure of A divided by the total pressure of the mixture is can be expressed in the sense using ideal gas law. The partial pressure of A is nothing but Na RUTM divided by Vm, and Pm we can write down as a Vm divided by Nm RUTM. You can cancel it out the terms, and you will also get this that which is the pressure ratio is equal to the mole ratio, that is Na divided by Nm, and which is nothing but your mole fraction, right, Ya, which is equal to the Va by Vm. From this we can conclude that the pressure fraction is equal to the mole fraction is equal to the volume fraction for an ideal gas. It won't be true for real gases, right. So, for mixture of 3 ideal gases, namely A, B, C, we can write down this mass balance we can do, and so also the mole balance that we have already done. And similarly, we can express the mixture pressure in terms of partial pressure of the 3 gases what we have considered in this example. So, as the volume is remaining same for all the 3 gases and so also the mixture, then we can calculate very easily the what we call internal energy of the mixture, which is nothing but summation of internal energy of A and B and C in this example, and that is we can generalize also this for the ith species. And of course, for this example is the 3 species, you can take n number of species, and which is nothing but Ni into Ui. Ui is the what we call mole internal energy or specific internal energy or internal energy per unit mole. Similarly, we can calculate the enthalpy, the summation of enthalpy of individual gases, and it can be expressed in terms of product of summation of or the summation of the Ni into Hi, right. And similarly, we can calculate the what we call entropy of the mixtures by knowing the entropy of individual gases, and you just sum it up and then you can get those values, right. So, now we will be we have till now discussed how to handle the ideal gas mixtures, but we will be discussing about how to handle the real gas mixtures. So, we know that the ideal gas law can be utilized for the real gas mixtures or real gas by just including a factor what we call is a compressibility factor. Look at this Zm is a compressibility factor, which we have already discussed earlier for a gas, and this Zm is the sum of product of compressibility factor of Ith, like of all the mixture components. So, Zm is basically summation of Yi and Zi. I is the ith species, and I can be 1 to like there might be several number of species. In this case, I is equal to 1 to n, like it may be 3 species, 4 species, 10 species, whatever it may be, but you need to find out individual compressibility factor and also the multiplied by the mole fraction, and sum over all the species will give you the mixture what we call compressibility factor. So, keep in mind that Zi has to be determined at the mixture what we call temperature and pressure for each individual components while using the Amagat law. See, that is a very important point you should keep in mind, right. What for determining the Z, what pressure and temperature you will have to take? Basically the mixture temperature and pressure, right. So, actually for evaluation of this JDEM, the Amagat's law is being preferred for high pressure gases over the Dalton's law, where you keep this basically what you call temperature and volume the same as that of the mixture while calculating, and because of it can give a better results. That is the reason why it is being used. And whenever you are using the low pressure gases, right, you can use the Dalton's kind of thing, but high pressure one has to go for the Amagat's law. So keep in mind that the compressibility factors do not predict the PVTV accurately for a mixture of gases, because of the effect of dissimilar molecules are not taken care by this, when you use this compressibility factor. So therefore, you will be incurring some kind of error even though you are using the compressibility factor for calculation or calculating the real gas mixtures properties, right. But however, we will live with that, because that error may not be that much for your engineering calculation particularly. So what we will be discussing is basically interested in to look at gas and vapor mixtures, right. And when we talk about this gas vapor mixture, we will be discussing basically the water and its vapor, like kind of things, because that is having applications for air conditioner kind of things. And because the air around us, whatever is there is a mixture of water and vapor, and of course the other gases like nitrogen, oxygen, other thing, because water is a part and parcel of us, and then particularly in the rainy season, like the air will be containing a lot of moistures, right. And moisture control is very essential for the maintaining a comfort, and also there are several other applications kind of things. So if you look at moisture content of the air is plays a very important role in several food processing industries, and then several drying processes kind of things. For example, if you want to dry this mango, what we keep it, or you want to have some, let's say, potato chips, like for your this thing. So you will have to maintain the water content, otherwise it will be difficult. So therefore we will be looking at it, but the gas vapor mixture in air conditioning systems, as I told, like is essential to be controlled, which in our country we do not do that because the costly affairs. What air conditioner we use is basically air cooler, it's not air conditioner. And when you talk about air conditioner, you will have to not only the control the moisture, but also the other obnoxious gases and which will be there. That means the quality of the air has to be controlled in case of air conditioning system, right. So which is a very costly affairs. But here what we will be discussing about the moisture content in a air, right. And as I told, it will be very essential for dryer and humidifiers, right, kind of things. So environmental control, as I told earlier, is very essential for human comfort, and also the smooth operation of the precision and costly machine use, particularly for scientific research. We get a lot of instruments from outside, we import it, but it won't work here because this is the very harsh environment in our country. It will be not only the moisture content will be fluctuating, and also the dust level and other gases. So we spoil the instrument very easily. Now we will have to maintain that. So that is also very important aspect of controlling the environment or the conditioning the air and kind of things. So what we will be doing, we will be using a very simplified model to analyze the gas vapor system by considering the following assumptions. That is, no dissolved gases in the solid or liquid phases are there, right. That we are considering. But however, one has to consider those things. Those are basically, has to be controlled so far good air conditioning is concerned. So gas power mixture can be treated as an ideal gas. And we can do that thing because the temperature range what we will be operating is very low, rather it is moderate, something 52 degrees Celsius on the one side, which is highest temperature one can think of, and also the minus 10 degrees Celsius we can think of kind of things. And therefore, we can very easily use that ideal gas, and we will be operating, we will be handling the atmospheric pressure so far air conditioning is concerned. So the equilibrium between the vapor at its condensed phase at a given temperature is not influenced by other component, right? That we are assuming, but in real situation it will be affected, right? If other constituents, are there, then their equilibrium condition, will be affected. And that means if you look at what we are doing, we will be using the partial pressure of the vapor, which is equal to the saturation pressure corresponding to temperature of the mixtures. Basically, we will be using that, you will be using that kind of things, and then so that we can handle. So before really getting into analyzing this air water vapor mixture, let us get acquainted with the terminologies what we will be using. So air conditioning, as I told earlier, that it is basically to handle the air water vapor mixtures and control it, right? That is the things. And because we will be controlling the moisture content in the air. And then when we talk about this air conditioning, we will be looking at basically one is dry air, other is the wet air. Of course, from the name indicates, it's very clear that dry air means it won't contain any kind of moisture. Moisture level will be 0, which is very difficult to get, particularly in our country. Okay? And wet air is the air with a certain amount of water vapor, and always will be there. If it is not there, let's say you imagine water vapor won't be there. What will happen? That means we will get dry skins. It is very difficult to maintain. Particularly we face this dry skin problem in old days and also in winter season, right? So therefore, we will have to maintain that. We need to understand the dry air and wet air. So in analyzing the air conditioning system, we should basically treat this atmospheric air as a mixture of dry air and water vapor. And actually it will be always wet, kind of air. You cannot get a 100% dry air unless you control it and then produce it, right? But atmospheric air always will be the wet air. Of course, the level of water moisture will be different depending upon the season, depending upon temperature, depending upon the conditions. So as I told earlier, the temperature of air in air conditioning application generally varies from something minus 10 degree to the 50 degree Celsius. So therefore, and also atmospheric pressure, right? So therefore, we can consider air as an ideal gas for analysis purpose without incurring much error, And water vapor can also be treated conveniently as an ideal gas with, of course, certain amount of error which is negligibly small, that is around 0.1%. We have seen that whenever there is a two-phase fluid, we cannot treat as an ideal gas. We have discussed enough. But in in air conditioning kind of thing system, like air water vapor mixtures is at 50 degrees Celsius, right? And the water vapor partial pressure corresponding to this 50 degrees Celsius will be around something 12.335 kilopascals. See how I will get this partial pressure? This is basically corresponding to the saturated pressure this is equal to the saturated paper corresponding to the 50 degrees Celsius. From the steam table you can get, very easily. So the pressure of atmospheric air with water vapor will be equal to what you call the P is equal to PA plus PWG. This is basically partial pressure of air, right? This is partial pressure of dry air, right? And this is the partial pressure of water vapor. This is partial pressure I am just writing, of water vapor. I have written Wg basically, it's a vapor. Right, that is the total pressure and is by the Dalton's law of partial pressure we are doing that. So, how to characterize the amount of water vapor in the air, that we need to look at it. So, we can talk that thing in terms of two quantities. One is relative humidity, other is the specific humidity, right. And if you look at the specific humidity is basically the ratio of amount of water vapor and the amount of dry air, the mass of the dry air. It is basically the ratio of the mass of water vapor and the mass of dry air. And I can write down that as by using the ideal gas law, that is PWG into V, volume is the same, into molecular weight of water into divided by RU1T. And similarly for air, I can write down the using ideal gas law, that is PA V molecular weight of air divided by RUT. If you look at like the same temperature, because the air will be at the wet air will be at same temperature, right. So therefore this will be cancel it out, right. If you look at, I can cancel this out, and similarly volume will be cancel it out, whereas molecular weight and of water divided by molecular air will give me 0.622, right, into PWG divided by PA, that is nothing but your specific humidity, right. So, if you look at the specific humidity of a dry air, what it would be? It will be what? 0, right. Dry air means there is no water vapor. So, therefore, it will be 0 because PW is 0, therefore, then the specific humidity will be 0. If water vapor is added to dry air, then specific humidity of course will increase, right, till what? Till it attains the saturated condition, right. And once it's saturated, you cannot really change that unless you change the temperature, right, because in atmosphere you cannot really change the pressure that much, but temperature can go up. So therefore, we need to know that what is the relative humidity. And let us take an example of air conditioning moisture, air containing moisture at 30 degrees Celsius, 100 kilopascals. And if you look at PS, PW, that is the partial pressure of the water at saturated condition, is basically 4.243 kilopascals, right. And this you can get from the where? From your saturated steam table corresponding to the 30 degrees Celsius. Okay. And if PW in the air or the wet air is less than 4.243, then it will be unsaturated air. That means it can carry more amount, some amount of air. But if it is equal to that, then it cannot really take, and that is the saturated condition. But if PW is equal to 4.243 kilopascal, then it is saturated air, right. So therefore, we need to look at the, define a quantity which will tell us how much air can carry water moisture corresponding to the what you call saturated condition. So, that will be the relative humidity, which we will be discussing in the next class more elaborately, and we will be trying to relate the specific humidity with the relative humidity, so that we can see how we can control and other things. Thank you very much.